Welcome to Brain Vision.
Hey guys, let's do problem 97. In this problem, we need to calculate what is the gauge pressure and temperature of gas. The component of the gas are nitrous oxide and nitrogen. Their molar mass, critical temperature and critical pressure we can find from the chart. The process temperature is given as 24 degrees Celsius. Let's convert it to Kelvin scale. Now we can calculate the pseudo-critical temperature, which is the mole fraction of one component multiplied by its critical temperature plus mole fraction of another component multiplied by critical temperature of that. Mole fraction of nitrous oxide is 0.1. And mole fraction of nitrogen is 0.9. Therefore, the pseudo-critical temperature is 144.5 Kelvin, and the pseudo-reduced temperature is the process temperature divided by the pseudo-critical temperature. Therefore, pseudo-reduced temperature is 2.06. Now let us calculate the pseudo-critical pressure. The pseudo-critical pressure is 37.3 atmospheric pressure. Now we need to calculate the average molecular weight of the gas mixture and the specific molar volume. Let us do that. The average molecular weight of the gas mixture is the mole fraction of nitrous oxide multiplied by its molecular weight, which is 44.02 kg per kilomole of nitrous oxide plus 0.9 mole of nitrogen per mole of gas multiplied by its molar mass, which is 28.02 kg per kilomole. Therefore, the average molecular weight of the gas mixture is 29.62 kg per kilomole, and the number of moles in 5 kg is N is equal to number of moles mass divided by molar mass. The mass is 5 kg, molar mass 29.62 kg per kilomole. Therefore, the number of moles is 0.169 kilomole. Now we can calculate the molar volume. The molar volume is equal to volume of the cylinder divided by the number of moles. Volume of the cylinder is 30 liter. Number of moles is 0.169 kilomole. Therefore, the specific molar volume is 178 liter per kilomole. Now let us calculate the ideal reduced volume, which is the specific molar volume multiplied by the critical pressure divided by gas constant multiplied by the reduced temperature. The pseudo-critical temperature is 37.3 atmospheric pressure. Gas constant is 0.0821 multiplied by 10 cube liter atm kilomole inverse 1, Kelvin inverse 1, and the pseudo-critical temperature is 144.5 Kelvin. Therefore, the ideal reduced volume is 0.56. Now for the reduced temperature of 2.06 and reduced volume of 0.56, the Z factor is 0.97. Now we can use the compressibility factor equation of its state to calculate the pressure. The number of moles is 0.169 kilomole. Let's convert it to mole by multiplying 10 cube. Gas constant is 0.0821 liter atm, mole inverse 1, Kelvin inverse 1. Temperature is 297 Kelvin and the volume is 30 liter. Therefore the pressure we get is 133 atmospheric pressure. Now this pressure is absolute. We need to get the gauge pressure, therefore we need to subtract 1. The gauge pressure is equal to absolute pressure minus the atmospheric pressure. Therefore the gauge pressure of the cylinder gas after the tank is filled is 132 atm. Next we need to calculate the temperature before the rupture. Now at the point of rupture, the absolute pressure is the sum of the gauge pressure plus the atmospheric pressure. The gauge pressure is 273 and the atmospheric pressure is 1. Therefore the absolute pressure is 274 atmospheric pressure. We know the pseudo reduced pressure at 274 atm. The pseudo reduced pressure at 274 atm we can calculate using the K's rule. The pseudo reduced pressure is 7.3. Now for this pseudo reduced pressure and the reduced volume of 0.56, Z factor is 1.14. Again we can use compressibility factor equation of its rate and calculate the value for temperature. Therefore temperature is equal to PV divided by Z in R. Let's insert all these known values. 274 atm multiplied by 30 liter divided by Z factor 1.14 multiplied by number of moles, which is 0.169 multiplied by 10 cube mole, and the gas constant is 0.0821 liter atm, mole inverse 1, Kelvin inverse 1, and from here we get the temperature as 520 Kelvin. Let's convert it to Fahrenheit scale. 520 to the Celsius scale, 520 minus 273 degrees Celsius, which is 247